Previously, we saw that for a number field K, Takagi has defined the notion of a Ray class field of K. This is a generalization of the notion of cyclotomic field. Recall that by Kronecker-Weber, every finite abelian extension L of Q is gonna lie inside some cyclotomic field. Similarly, every finite abelian extension L of a number field K is gonna lie inside some Ray class field of K. These allow us to generalize the notion of a conductor of a finite abelian extension L over Q to a finite abelian extension L over a number field K. Recall that the conductor of L over Q is the smallest integer m, such that L lies inside the m cyclotomic field. Thus, we can define the conductor of L over K to be the smallest modulus m, such that L's lie inside the Ray class field with modulus m. Now, in this video, we want to talk about the relationship between conductor and ramification. Recall that if P is a Q prime, then P ramifies in L if and only if P divides the conductor of L over K. The same thing holds for the case of a finite abelian extension of a number field K. If P is a prime of K, then we have P ramifies in L if and only if P divides the conductor of L over K. So let us have a look at an example. Let us find the conductor of L over K in the case when K is just Q and L is Q adjoint I. Note that 2 is the only prime of Q ramifying in Qi. So we would expect that the finite part of the conductor consists only of powers of 2. And indeed, we'll see that it's exactly gonna be 4 times the infinite prime. Alright, so how do we go about finding the conductor of L over K? Well, the only thing we have so far is the definition, so maybe let's use the definition. The conductor should divide all admissible modulus, so let's find an admissible modulus. Recall that previously we have shown that Qi is a class field over Q with respect to the modulus 4 times the infinite prime. That is because in that case, we have computed the norms. And so we saw that the norms of fractional ideals are just gonna lie inside Pm. Thus, this norm subgroup must be equal to Pm, because remember, this was defined to be the product of those norms with Pm. Therefore, the index of the norm subgroup inside Im is just gonna be equal to the index of Pm inside Im. Now we know that in that case, the ideal class group Im quotient by Pm is just gonna be isomorphic to Z mod Mz star, i.e. Z mod 4Z star. So thus we have that this index is just going to be equal to the size of Z mod 4Z star, which is 2, and that is equal to the degree of Qi over Q. So then, by Takagi's definition of class field, we have that Qi is going to be the class field with respect to the modulus for infinity. Now, that means that Qi must lie inside the Ray class field corresponding to the modulus 4 times infinity. In other words, 4 times infinity is an admissible modulus of Qi over Q. Therefore, the conductor of Qi over Q must divide 4 times infinity. So we have 3 possibilities. It could be 2 times infinity, or 4 times infinity. So let's consider the first possibility. For the conductor to be 2 times the infinite prime, this modulus has to be first of all admissible. In other words, we must have that the degree of L over K, Qi over Q, must be equal to the index of the norm subgroup with respect to the modulus m inside Im. However, the index of p to infinity inside I to infinity is gonna be equal to 1, and that's not equal to 2. So this means that this modulus is not admissible, and thus the conductor is not equal to 2 times infinity. So let us see why that is, that this index here is equal to 1. Okay, so let's figure out what I to infinity is. Now, since Qi has class number 1, all of the fractional ideals and I to infinity are gonna be principal fractional ideals, and they are gonna be generated by A over B, where A, B are integers prime to 2, i.e. they are both odd. Now, if A over B is a generator, then minus A over B is also a generator. So we can always choose a generator, alpha over B, such that alpha and B have the same sign, right? And alpha and B are congruent to 1 modulo 2. Well, this set is by definition just equal to p to infinity, and thus we have that I to infinity is equal to p to infinity. Therefore, this quotient here is trivial, and thus this index is equal to 1. Thus this index is not equal to the degree of Qi over Q, so this modulus 2 times infinity is not admissible. Similarly, we'll see that the modulus 4 is also not going to be admissible because I4 over P4 has size 1, which is not equal to the degree of Qi over Q. This is because, again, I4 is the set of all fractional ideals generated by A over B that are prime to 4. Now again, if A over B is a generator, then so is minus A over B. Therefore, by changing a sign, we can assume that alpha and B are congruent to the same thing, modulo 4. So because if A is already congruent to B modulo 4, we just let alpha be equal to A. Otherwise, then we just let alpha be equal to minus A, because A and B can only be congruent to 1 or 3 modulo 4. And thus we get that I4 is just going to be equal to this set here, which is just P4. Therefore, I4 over P4 is equal to 1 as claimed. Observe though that what we did here would have not been possible if we require that alpha and beta have the same sign, i.e. if we have used the modulus for infinity. Because then in that case, 1, we have chosen a generator, A or minus A, such that it's the same sign with B. We can no longer switch it so that A and B have the same residue, modulus 4. Alright, so we saw that we have eliminated the possibility that the conductor of L over K is 2 times infinity or 4. Now, again, because we said that it must divide 4 times infinity, therefore, the only possibility is that this conductor is actually 4 times infinity. And thus we have that this conductor is 4 times infinity. And indeed, the primes dividing these are exactly those that ramify, i.e. exactly the prime 2. Now, the fact that the conductor capture ramification suggests that there must be some relationship between the conductor and the discriminant. And indeed, for a finite abelian extension of a number field K, we'll see that the discriminant and the conductor of L over K are gonna have the same prime factors. This is because they're both gonna be product of these conductors of characters. So let us define what these conductors are. Now, let M be an admissible L over K modulus. Then, for every character on the generalized ideal class group modulo M, we can define a corresponding class field. Namely, this is the class field corresponding to the kernel of the character. The conductor of chi is then just defined to be the conductor of the extension of this class field over K. It turns out that the discriminant of L over K is just gonna be the product over all these conductors, actually over all the finite part of these conductors. whereas the conductor of L over K is just gonna be the least common multiple of these conductors. For example, when the degree of the extension L over K is 2, then the discriminant of L over K is just gonna be the finite part of the conductor of L over K. In particular, when K is Q and L is just a quadratic number field over Q, then since we know the discriminant of such a number field, we know the finite part of the conductor of such a number field. In all of these cases, the full conductor, including the infinite part, must divide this absolute value of 4D multiplied with the infinite prime. That means that this modulus must be an admissible modulus for Q adjoint square root of D. Finally, we just want to make a quick remark. Now has proved this formula actually by using a decomposition of the zeta function for L into a product of Weber zeta functions for the character of this generalized ideal class group. We'll go into more details when we discuss the L functions. But first, next up, let us come back to Hilbert's conjecture. In the next video, we're gonna show that the Hilbert class field as constructed before is the maximal unramified abelian extension of K.